Welcome to Homework Lib.
This problem is slightly tedious, but it's not hard at all. So instead of doing every minute calculation, I will keep things as general as possible and give the results. So, in effect, this is sort of approximating an experimental technique. So, you measure in the problem, you've measured the rotational spectrum of hydrogen chloride, and that you find certain wavelengths among the spectrum uh, from 60.4 micrometers all the way up to 120.4 micrometers. And the question tells you to use these measured wavelengths to find the moment of inertia of the hydrogen chloride molecule about an axis through the center of mass and perpendicular to the line joining them. So that's just to say, like what we've done before, as if you had a ball, two balls on a string, all rotating around this axis, going like this. So the moment of inertia is typically, if you had the masses and separation, it would just be the reduced mass times r squared. But we're being asked to find it just through this data. And that might seem like it's going to be a difficult task, but in reality, if you think about the rotational energy at a given state, EL, it's equal to L times L plus 1 times h bar squared over 2I. And there it is. There is the moment of inertia that we want to find. But it's a little tricky because we don't necessarily know what levels these are right off the bat. So it's not like we can just brute force calculate everything and have it work out. However, if we figure out a sort of slope of this line, a average separation for them, that will actually tell us this constant factor here, h bar square over I. So if you calculate the average spacing and energy of these, which we can get their energies by the tried and true formula of Planck's constant times the speed of light over the wavelength, and then we calculate some E average, this should be roughly equivalent because there might be experimental errors to h bar square over I. And if you do this, again, it's very straightforward just to do the calculation aspect of it. Sum them up and divide by 5. You get an energy average of 0.410 times 10 to the minus 21 joules, and have this equal to h bar squared over I. Do a little shuffle, and you get that I, the moment of inertia, is 2 2.71 times 10 to the minus 47th power, and the units there are kilogram meter squared. All right, great. So this is actually very close to uh, the quote real value, which you may have seen elsewhere in the text already, because carbon monoxide has been used quite a bit, or sorry, hydrogen chloride has been used quite a bit. So you may be able to compare it with accepted values. But that is just part A. And part B tells us that the value of L changes by plus or minus 1 in rotational transitions. So there's no jumping. There's no jumping from L equals 2 all the way to L equals 9 or anything like this. And it wants to find what value of L for the upper level of the transition gives rise to each of these wavelengths. So for this one, we can leave this page for now, but we'll leave the wavelengths written here just to do a little bit of scratch work on a new page. So if we have that L changes by plus or minus 1, then you get that each level will have a difference of L times L plus 1, subtraction for the difference in level, L minus 1, because it's L minus this one, times L, because it's L plus 1 minus 1. So again, this is EL minus EL minus 1. And this is all multiplied by h bar squared over 2 times the moment of inertia. If you work this out, though, you see that this just gives 2 times L times h bar squared over 2I. Those 2's will cancel out. So each level has an energy LH bar squared over the moment of inertia. But it wants us to find a value of L for each of those transitions, or for each of those wavelengths on the previous page. So it might be smart to derive some sort of equation for a given L. So if that's our energy, then if we take the fact that our energy of the photon can be written like this, then we can set these to be equivalent. And we want to solve for L. So L is equals to h bar c over, or sorry, that's just normal h bar square times lambda. But h bar and h bar square, or sorry, h and h bar have some similarities because h bar is equal to h over 2 pi. So one of these h's is going to cancel. Thus, you can write it as 2 pi c times the moment of inertia, because I forgot to move that over, divided by h bar lambda. And then finally, if you plug in for all the constants and the values that we know, so that, and that, you get a value 4.8 3 times 10 to the minus 4. And the units here are likely meters. I'd have to recheck my work there, but all divided by the wavelength. And so finally, if we go and just plug in the wavelength from the previous page into here, then that will give us, to the nearest integer, you have to round what your L's are. So if I go back to the previous page, we can say that this is L equals 8, this is L equals 7, L equals 6, L equals 5, and finally L equals 4. All right, but now the question asks still more from us. C, it wants us to use our result from part A, which is here, to calculate the equilibrium separation of the atoms in the hydrogen chloride molecule. But luckily, I already wrote down the relation here, and we have this, and the reduced mass is just mass 1 times mass 2 over their sum. So for C, and this is B, we can just plug in to solve for R. And if you do the math there, you get that it is 0.129 nanometers. And then finally, part D, what is the longest wavelength line in the rotational spectrum of hydrogen chloride? So this one you can figure out after thinking on it a little bit, but the longest wavelength, so we can go to a new page yet again. The longest wavelength corresponds to the lowest energy. Because for light, as wavelength goes up, energy goes down. So then the way that we can figure out the longest wavelength line in the rotational spectrum of hydrogen chloride, we need to look at the lowest energy rotational spectrum. And that is, of course, the transition from EL equals 1 to EL equals 0. And the energy of this one is simply h bar squared over I, the moment of inertia. And if you calculate the energy, you get that it is 4.099 times 10 to the minus 20, 25, I believe. I'm just going to recheck that to make sure that I don't have an error. And then, oh, sorry, that is joules. And you can calculate the wavelength by hc over E or delta E in this case. And the wavelength is 485 micrometers. And so the main trick about a problem like this is that you are going to have a it seems like it's very daunting, but in reality the uh, most of the work is done once in solving for the equations that will allow you to quickly calculate the rest of the problem. So the primary thing to take away from a problem like this is that one, make sure you get your values right. This is a 2, not a 5. And to make things as simple as possible for yourself moving forward with this long problem. So we'll call it quits there.